8%. Let that number sit for a moment before we go anywhere else with it. Not 8% chance of rain, not 8% below average, relative humidity, 8%. The actual moisture content of the air measured this morning across Wyoming, Colorado, Nebraska and New Mexico simultaneously. Across all 4 states at once, the sensors are returning the same number, and the number is 8. Here is the first thing you need to understand about that figure. The Sahara Desert, the canonical reference point for planetary aridity, carries a long-term average relative humidity of around 25%. Death Valley, the hottest place in the Western Hemisphere, the floor of a below-sea-level basin baking under the Mojave sun in the middle of August, typically reads somewhere around 10% at its worst. The threshold below which fire scientists describe ignition as almost trivially easy as 15%. We are at 8. Not near 8. Not approaching 8. At 8, across a multi-state geographic footprint covering hundreds of thousands of square miles of continuous grass and shrubland on a morning in late March. Stay with me here, because this is where the investigation begins. The sensors are not malfunctioning. This is not a forecast artifact, not a rounding error, not a model output that someone accidentally pulled instead of a field reading. Multiple independent monitoring networks across 4 separate states are converging on the same number this morning, and that convergence is itself a signal. It means the atmospheric state producing this reading is spatially coherent across an enormous area, not a local anomaly generated by a single dry air mass sitting over a single basin. The dryness is everywhere at once. To translate 8% humidity into physical reality, you need to think about what moisture does inside a plant at the cellular level. Fine fuels, meaning grass blades, surface litter, the accumulated dead material sitting in mats across the landscape, maintain internal cellular moisture that acts as a thermal buffer. When you introduce a heat source to fuel with normal springtime moisture content, the water inside those cells has to be driven off before the material can reach ignition temperature. That process absorbs energy, it slows the reaction, it raises the thermal threshold the fire has to overcome. At normal spring humidity levels, a fire has to do real work to get started and real work to keep going. At 8% relative humidity, that buffer is gone. Research published in fire science literature documents that ignition, temperature for fine fuels drops by roughly 30 to 40 degrees Celsius when humidity falls below 10% compared to fuels at normal springtime moisture content. Think about what that actually means in mechanical terms. A spark, a cigarette, a downed power line, a piece of metal scraping against asphalt, any of these creates a heat pulse. Under normal conditions, that heat pulse has to climb a temperature threshold high enough to drive off cellular water before it can sustain combustion. At 8% humidity, the threshold is 30 to 40 degrees lower. The gap between a transient spark and a sustained ignition, which is normally a meaningful physical barrier, has been compressed nearly to nothing. And here is the part that makes this operationally dangerous in a way that a simple humidity reading does not fully communicate. You cannot see this. A grass field at 8% humidity and a grass field at 25% humidity look identical to the human eye. Both look like dry March grass. The difference is invisible. The difference is entirely contained in the cellular moisture of material that appears identical under any visual inspection. The landscape does not announce that it has crossed the threshold. It simply waits. Now overlay the geographic scale. This is not a single ridgeline, not a single drainage basin, not even a single state. The 8% reading is simultaneous and coherent across Wyoming, Colorado, Nebraska, and New Mexico. That is roughly 1,400 miles of continuous terrain measured along the north-south axis alone. Fine fuels exist at sub-ignition moisture thresholds across an area that, if it were a country, would rank among the larger nations on Earth by land mass. Every acre of that terrain is sitting at the same pre-ignition threshold at the same time. The National Interagency Fire Center, which coordinates wildfire suppression resources across the continental United States, has never in its institutional history issued the language it is issuing this morning for the month of March. That is not an informal observation. That is a documented departure from the entire operational record of that agency. The Storm Prediction Center is carrying critical fire weather risk designations that extend not just across the expected western and plains geography, but anomalously to New York and Georgia, a geographic spread of fire weather concern that has no precedent in March. Wyoming utilities are cutting power preemptively this morning, making a calculated decision to absorb certain and quantifiable economic losses from planned outages in order to reduce the probability of power line contact with fuels that are sitting below ignition threshold. These systems are not reacting to a fire. There is no fire yet. All of them are reacting to what exists before the first spark. But here is where the investigation demands more than a description of the present reading. Because the question that the data immediately raises and does not answer by itself is this: how does a landscape that was recording multi-year precipitation surpluses arrive at a fire threshold that exceeds Death Valley in August, and what physical chain made that possible in March? That question is not rhetorical. It has a specific, traceable, mechanistic answer, and that answer is not simple, and it does not begin with the humidity sensors. It begins much earlier, in a set of decisions the atmosphere made across a sequence of months, and the uncomfortable finding that emerges when you actually run the chain is that the 8% reading is not a surprise if you know where to look. It is, in a very specific and verifiable sense, a predictable terminal output of a sequence that was already underway. The first step in that sequence is the one that will feel most counterintuitive, because it begins not with dryness but with abundance. It begins with the years when the rain came, the grass grew tall, and the region's ecological health indicators were trending in a direction that looked, from the outside, like good news. The instinct in that scenario is to feel safe, to feel as though a well-vegetated, well-watered landscape is a protected landscape. The data from the past 3 growing seasons across the Great Plains and the Intermountain West tells a different story entirely. And that story begins with a principle at the center of fire ecology that inverts almost every assumption you bring to the subject. The instinct runs deep. A landscape that has received abundant rainfall feels like a protected landscape. A region where grasses grow tall and shrubs expand their range, and the soil holds moisture through the summer, feels like a region that has earned some buffer against the worst outcomes. When precipitation surpluses persist across multiple consecutive years, the mental model that forms both in public perception and sometimes in resource allocation is one of ecological resilience. The land is healthy, the land is full, the land is safe. The fire ecology data from the 2023 through 2025 growing cycle across the Great Plains and Intermountain West does not support that mental model. It systematically dismantles it. Here is the principle you need to hold in your mind for everything that follows, because it inverts almost every intuition you bring to the subject. A wet year does not protect a landscape from fire. A wet year loads a landscape for fire. The precipitation surplus and the fire risk are not opposites sitting at 2 ends of a spectrum. They are sequential partners in the same process, one following the other as reliably as spring follows winter, provided the atmospheric conditions cooperate at the right moment. The mechanism works like this. During a multi-year wet cycle, vegetation responds to available moisture in the way that vegetation always responds. It grows. Grasses develop denser root networks, produce more above-ground biomass, and achieve heights and coverage densities that significantly exceed what a normal rainfall year would support. Shrubs expand laterally into terrain they could not colonize during drier periods. Annual plants complete their life cycles and deposit seed banks and organic debris in quantities proportional to how productive the growing season was. Perennial grasses put down carbon reserves that support more vigorous spring growth the following year. All of this is ecologically normal and, by the standard metrics of land health, genuinely positive. But every gram of that biomass is also, in the language of fire science, fuel, not a threat yet, not dangerous in its living state, but a physical quantity of combustible organic material that now exists on the landscape and did not exist before the wet cycle created it. Fine fuels meaning grass blades and annual plant residue, medium fuels meaning shrub branches and accumulated litter layers, and the continuous surface connection between them have all increased in density, coverage, and spatial continuity. The landscape has been stocked. Now, the wet cycle ends, or in this case, it ends, and is replaced by something far more abrupt than a gradual return to average precipitation. But set aside the speed of the transition for a moment, and focus purely on the structural situation the landscape enters when the moisture begins to decline. What the drying atmosphere encounters is not the sparse, patchy, fuel-limited terrain of a landscape that has been managing through chronic aridity. It encounters a dense, well-connected, spatially continuous fuel bed that 3 years of productive growing seasons have built and maintained. Every wet growing year added another layer to what fire scientists would describe, without any rhetorical exaggeration, as a combustion library. Volume, continuity, fine fuel surface area, and the organic debris accumulation that forms the ignition bridge between the surface and the canopy, all of it present, all of it waiting for the moisture to leave. The growing season data from this period supports this in specific terms. Across the central and southern Great Plains, the Normalized Difference Vegetation Index, which is the satellite-based measure of surface greenness and vegetation density, was running above the long-term mean for 3 consecutive growing seasons through the summer of 2025. In portions of southeastern Wyoming and northeastern Colorado, above-ground grass biomass estimates from rangeland monitoring networks were reaching levels associated with what land managers sometimes call exceptional forage years, meaning grass production that exceeds average by a margin, large enough to drive significant optimism in the agricultural sector about carrying capacity and livestock forage availability. That optimism was not misplaced relative to the grazing question. It was simply not asking the right question about the fire question. Shrub encroachment data from the same period shows expansion of sagebrush and rabbitbrush into terrain along the Colorado Plateau and Wyoming Basin that had been functionally shrub-free during the preceding dry cycle. Shrubs matter in this context for a specific reason. Grass fuels are fine fuels, meaning they ignite readily, but burn at relatively lower intensities. Shrubs function as what fire ecologists call ladder fuels, providing the vertical fuel continuity that allows surface fire to climb into taller vegetation and produce higher intensity combustion. A landscape with dense grass and significant shrub encroachment is not just a landscape with more fuel, it is a landscape with a more connected fuel architecture, one in which fire can transition between fuel types more easily and sustain itself through terrain that might otherwise have interrupted its spread. Organic debris accumulation compounds this. Each productive year deposits a litter layer at the soil surface, dry plant material that did not fully decompose over the winter. Under normal conditions, decomposition organisms work through this layer during the moist months, and the accumulation does not reach levels that dramatically alter the fire environment. But when the wet cycle is followed by an abrupt and severe drying event, that decomposition process slows and then essentially stops. The litter layers from successive productive years remain intact, stacked, and increasingly dry. They become the surface fuel that connects grass patches, that carries fire across terrain gaps that would otherwise break continuity, and that produces the sustained low-level combustion that makes suppression on the ground particularly difficult. This is the state the landscape of the central and intermountain region entered at the beginning of 2026, not depleted, not sparse, fully stocked, architecturally connected, and sitting with a multi-year fuel debt that no amount of pre-ignition optimism was going to offset once the moisture began to drain. Think about what that actually means for the risk calculus. Standard fire season preparedness frameworks tend to treat high fire years as years that follow drought years, which is an accurate but incomplete description of the mechanism. What the biomass data from this period illustrates is that the drought year is not generating the fuel. The wet years before it generated the fuel. The drought year is providing the ignition environment. These are two separate contributions to the same outcome, and they require two separate sets of conditions, which is precisely why the combination is so operationally difficult to anticipate using frameworks that treat fuel load and moisture deficit as a single variable. Stay with me here, because this is where the data starts to demand a question that the fuel loading story alone cannot answer. The fuel architecture described above, that multi-year biomass surplus distributed across millions of acres, represents the potential energy stored in the system. Potential energy does not become a fire problem until the conditions that activate it arrive. And what arrived in the winter of 2025 into 2026 was not a gradual drying, not a slow seasonal transition towards summer aridity, not the kind of moisture decline that the landscape and the monitoring systems have historically had months to process and respond to. What arrived was something structurally different, driven by an atmospheric failure at an elevation and altitude that most people never think about when they think about weather, and whose consequences cascaded downward through every layer of the physical system between the stratosphere and the soil. The question is not just why the fuel was there. The fuel being there is now fully explained. The question is what mechanism was large and persistent and anomalous enough to remove the moisture from that fuel at a rate and a scale sufficient to produce 8% relative humidity in March across 4 states simultaneously. That mechanism did not originate at the surface. It originated tens of miles above it. The mountain is supposed to hold the water. That is its function in the hydrological system, and it has performed that function reliably enough across the instrumental record that an entire civilization of water management in the American West was engineered around the assumption that it would continue to do so. Reservoirs, irrigation schedules, municipal water contracts, agricultural planting calendars, the operational timelines of every water district from Denver to Albuquerque, all of it rests on one foundational premise: that precipitation falling on high elevation terrain in winter will be stored as snow and released slowly, predictably, over the weeks and months that follow. The snow water equivalent data coming out of Colorado and Utah this winter has something to say about that premise. Snow water equivalent is the standard metric hydrologists use to express what is actually stored in a snowpack, not the depth of snow, which can be misleading because snow density varies enormously depending on temperature and precipitation type. Snow water equivalent converts the snowpack into the volume of liquid water it contains, which is the number that actually matters for downstream hydrology. A deep, fluffy snowpack at low density might contain far less water than a shallower, denser pack. Snow water equivalent cuts through that ambiguity and tells you what you have in real terms. What the monitoring networks across Colorado and Utah are telling you right now is that snow water equivalent across both states is at the lowest level recorded in the instrumental record. Not the lowest in recent memory, not the lowest in a decade, the lowest in the record, full stop. And over 80% of the individual monitoring stations across the broader region are reporting below normal figures. This is not a spatial average being pulled down by a few outlying stations in an otherwise normal distribution. The anomaly is spatially coherent across the entire mountain system. Now here is the part that requires some careful thinking, because the intuitive explanation for low snowpack is simply that it did not snow enough, and that explanation is not wrong exactly, but it is incomplete in a way that matters enormously for understanding what happened to the soil moisture base entering spring. The proximate physical cause of the snowpack failure this winter was not a simple absence of precipitation events. The cause was a displacement of what meteorologists call the rain-snow line, the elevation threshold above which falling precipitation is cold enough to arrive as snow rather than rain. In a normal winter, that line sits at an elevation determined by the average temperature profile of the atmosphere above the mountain terrain. Precipitation falling above the line accumulates as snow and stays there, building the seasonal reservoir. Precipitation falling below the line becomes rain and enters the surface runoff system within days. What happened this winter was that anomalous warmth throughout the lower and middle atmosphere pushed that line several hundred meters higher than the historical elevation norms for this region. Not slightly higher, substantially higher, persistently higher, across essentially the entire winter season. And that shift had a specific mechanical consequence. Precipitation events that under normal temperature profiles would have deposited snow on terrain at, say, 8,000 feet, were instead delivering rain to that terrain. The water arrived, it contacted the ground surface, and then, within 48 to 72 hours, it became surface runoff and left the system. Stay with me here, because this is where the hydrology gets genuinely consequential. The mountain received its moisture budget. That is the important thing to understand. The atmospheric systems delivered precipitation. The precipitation just could not be stored. Snowpack functions as a slow-release reservoir because it holds water in a frozen state through winter and spring, releasing it gradually through snowmelt as temperatures rise into late spring and early summer. The timing of that release is not random. It is remarkably consistent across decades of observation, driven by the predictable progression of seasonal temperatures. Water managers call this the delivery schedule, and entire infrastructure systems were built to absorb that water at the times and volumes the snowpack historically provided. When precipitation falls as rain instead of snow at those elevations, the delivery schedule disappears. All of the water that would have been held in cold storage and released over 12 to 16 weeks instead arrives in the drainage basin within 2 or 3 days of the precipitation event. The soils receive a brief pulse of moisture, the streams run high for a short period, and then the water is gone downstream. The reservoir that was supposed to be filling with frozen water through November, December, January, and February is empty, and the soils entering spring carry a deficit they would not normally encounter until the middle of summer. Hydrologists have a name for this mechanism. They call it the hydrological time shift. The total annual precipitation budget has not necessarily declined in the way that simple drought usually implies. What has changed is when the water is available. The shift compresses the delivery of winter precipitation into a narrow window at the surface, while eliminating the extended slow-release function of snowpack entirely. The practical result for any system depending on spring and early summer soil moisture is that the calendar of moisture availability has been rewritten. Mid-July soil moisture conditions are arriving in March. The landscape is running more than 3 months ahead of its historical moisture schedule. If you want a concrete sense of the magnitude of what that means, consider this. In a normal hydrological year across this region, soils are still receiving meltwater inputs through May and into June. Grasses that green up in April are doing so into terrain that still has a moisture credit from winter snowpack. The critical fire weather window, the period when fine fuel moisture drops below dangerous thresholds, historically opens in late June and July as snowmelt ends and summer heat builds. That is the window suppression agencies prepare for. That is when the air tankers are pre-positioned and the crews are fully mobilized. The hydrological time shift has moved that window, not shifted it slightly, moved it by months. The soil moisture deficit that historically required the combined work of summer heat and evaporation running through June to produce is already present in the 3rd week of March. And the fine fuel moisture content that follows soil moisture with a lag of days to weeks is already below the thresholds that the historical calendar would have placed in midsummer. Now add the January data at the continental scale, and the picture sharpens further. The National Oceanic and Atmospheric Administration's satellite-based monitoring network, which has tracked continental snow cover extent across North America since 2001, recorded the lowest continental snow cover extent in the entire history of that monitoring program in January of this year. 25 years of satellite data and the January 2026 reading cites below every previous value in the record. That is not a regional anomaly. That is a continental scale signal expressed simultaneously across the mountain systems and the northern plains and the Great Basin, all of it pointing to the same underlying atmospheric forcing. Think about what that actually means for the investigation. If the snowpack failure were a regional event driven by a local precipitation deficit, you would expect to see spatial variability. Some basins anomalously dry, others closer to normal, the kind of patchy pattern that localized atmospheric dynamics tend to produce. What the continental snow cover data shows instead is spatial coherence, meaning the same forcing mechanism was operating at a scale large enough to suppress snow accumulation across essentially the entire northern half of the country simultaneously. That is not the signature of local variability. That is the signature of a large-scale atmospheric anomaly operating at the level of the full continental circulation. And that is the question the snowpack data is now asking. What was large enough and persistent enough and anomalous enough to displace the rain-snow line across an entire interconnected mountain system for an entire winter season, while simultaneously suppressing continental snow cover to record lows from one coast to the other? The answer is not in the clouds that dropped the rain instead of the snow. It is not in the surface temperatures that were too warm to freeze it. It is in an event that most people have never heard of, operating in a layer of the atmosphere so high above the surface that it rarely enters public discussion, that occurred in January and whose consequences cascaded through every layer of the physical system between the upper atmosphere and the soil. The atmosphere broke first at altitude. Everything else followed from there. 40 miles above the surface of the Earth, in the layer of atmosphere called the stratosphere, something happened in January that most people were not aware of, and that most weather reporting did not cover. It was not a storm. It was not a precipitation event. It produced no winds at the surface, no clouds visible from the ground, no readings on any instrument you would encounter in daily life. But what it set in motion filtered downward through the entire column of atmosphere above the central United States over the weeks that followed, and its fingerprints are present in the snowpack failure, in the soil moisture deficit, in the rain-snow line displacement, and ultimately in the 8% humidity reading that opened this investigation. The event is called a sudden stratospheric warming, and to understand why it matters, you first need a working model of what the stratosphere is doing under normal conditions. The polar vortex is not a media invention. It is a real and persistent atmospheric feature, a large-scale cyclonic circulation centered over the poles that exists because of a temperature gradient. The core of that gradient is the difference between the extremely cold air over the polar region and the warmer air at middle latitudes. That temperature contrast sustains a strong band of westerly winds encircling the pole at stratospheric altitudes, and those winds act as a containment wall. They keep the coldest polar air locked over the high latitudes. They also, critically, influence the behavior of the jet stream in the troposphere below, the river of fast-moving air at altitudes more relevant to weather systems. A strong, intact polar vortex tends to keep the jet stream in a relatively tight, fast-moving circular pattern around the middle latitudes, one that efficiently steers storm systems across the continent and delivers moisture to the regions that depend on it. Now here is what a sudden stratospheric warming event does to that structure. Through a mechanism involving atmospheric waves generated in the lower atmosphere propagating upward into the stratosphere, a large pulse of energy can be injected into the polar stratosphere over a period of just a few days. When that happens, stratospheric temperatures over the pole rise by 30 to 40 degrees Celsius within that same brief window, 30 to 40 degrees in a matter of days, at an altitude where the baseline temperature is deeply below freezing, driven not by surface heating but by wave dynamics operating in the upper atmosphere. The temperature gradient that was holding the polar vortex together collapses. The vortex weakens, distorts, and in the most pronounced events can elongate dramatically or split into multiple smaller vortices that migrate toward the middle latitudes. This is what happened in January of this year. A sudden stratospheric warming event of significant magnitude disrupted the polar vortex during a period when the mountain snowpack across the western United States was still in its critical accumulation phase, the weeks when the difference between a strong snowpack year and a deficit year is largely determined. Stay with me here, because the connection between the stratosphere and the snowpack runs through the jet stream, and the mechanism is specific. When the polar vortex weakens, the tropospheric jet stream below it loses its organizing constraint. Instead of flowing in a relatively tight, fast-moving circuit, it develops what meteorologists call high-amplitude patterns, large north-south undulations that produce persistent ridge and trough structures across the continental geography. Two specific types of these patterns are particularly relevant. The first is called an omega block, named for the shape the upper-level wind pattern forms when mapped on a pressure chart, a large ridge flanked by troughs on either side that resembles the Greek letter. The second is a Rex block, a stacked high-pressure system over a low-pressure system that produces similar flow stagnation. Both patterns share the same critical operational feature. They are slow to move. Where a normal, vigorous jet stream configuration steers storm systems through a region in a matter of days and then brings the next system behind it, a blocking pattern deflects those same storm systems to the north or south of the block. Precipitation that would have crossed the mountain terrain simply does not arrive. The storm track has been rerouted around the ridge. Following the January sudden stratospheric warming event, a blocking high-pressure ridge established itself over the western United States and remained there. Not for a week, not for 10 days, for an extended period that ran through what should have been the most productive snowpack accumulation weeks of the winter season. Storm systems crossing the Pacific were deflected northward into Canada or southward into Mexico. The moisture delivery that the mountain snowpack required to reach seasonal normal simply did not make it through the block. And simultaneously, the ridge brought anomalous warmth, the same warmth that displaced the rain-snow line upward by several hundred meters and converted the precipitation that did arrive into rain rather than snow. Think about what that combination means in physical terms. The sudden stratospheric warming event did not produce a single bad outcome for the snowpack. It produced two simultaneous bad outcomes working in the same direction. First, It reduced the number of storm systems reaching the mountain terrain by rerouting the jet stream around the blocking ridge. Second, the warmth associated with the ridge ensured that the precipitation events that did penetrate the block were more likely to fall as rain at elevations that would historically have received snow. Reduced storm frequency and reduced snow fraction per storm, both consequences of the same stratospheric forcing event, both compounding the snowpack deficit across the same accumulation window. The literature on sudden stratospheric warming events and their surface weather consequences is well established, and it is worth being precise about what that literature does and does not say. The connection between a sudden stratospheric warming event and subsequent tropospheric circulation anomalies is documented in the observational record and has been reproduced in atmospheric modelling. The typical lag between the stratospheric event and the emergence of recognisable surface impacts is on the order of 2 to 6 weeks, though that lag varies and is not perfectly predictable in any individual case. What the January event and the subsequent blocking pattern represent is consistent with the documented behaviour of stratospheric warming events and their downstream effects. It is not speculative to connect them. The mechanism is real. Here is where the investigation has to do something important, though. It has to ask a second-order question, because a sudden stratospheric warming event producing a blocking ridge that disrupts the snowpack is a known physical sequence. It has happened before. It will happen again. The question that the data from this particular event demands is whether this January event was operating in the same background atmospheric environment as previous stratospheric warming events, or whether it was being amplified by something larger, something operating at the scale of the global ocean rather than the scale of regional atmospheric dynamics. Look at what we know about the atmospheric state that surrounded the January event. The jet stream was already under stress from a La Niña pattern that had been running for 18 months, systematically biasing the storm track northward, across the southern tier of the United States. The background sea surface temperature field across the global ocean was running at levels without precedent in the instrumental record. These are not neutral background conditions against which a stratospheric event plays out in isolation. These are forcing mechanisms that were already pushing the atmospheric circulation toward persistent ridge patterns, already priming the western United States for below-normal precipitation, already loading the moisture deficit that the January stratospheric event then locked in place, and the subsequent March warmth then completed. The stratospheric event is the trigger mechanism in the middle of this chain, but it is sitting inside a larger atmospheric context that was already arranged to amplify its consequences, and that context begins in an ocean that has been doing something with no historical precedent for more than a year. The ocean's role in this chain is not peripheral. It is the background energy source against which everything else has been operating, and the data describing what that ocean has been doing reframes every other piece of this investigation. The tropical Pacific Ocean does not announce its phase transitions with any kind of drama. The shift between La Niña and neutral conditions, and eventually toward El Niño, happens through changes in sea surface temperature gradients, measured in tenths of a degree Celsius, tracked by a network of moored buoys drifting across a stretch of ocean that most people will never see. The Oceanic Niño Index, which is the formal measure of those anomalies, averaged over a defined region of the central and eastern tropical Pacific, has been returning toward neutral over recent months. Forecasters at the Climate Prediction Center are now discussing the possibility of El Niño development in late this year. From a certain perspective, this looks like good news. The pattern that has been suppressing precipitation across the southern tier of the United States for the past 18 months is ending. Here is what that framing gets wrong. La Niña does not end its drought the way you turn off a faucet. The ocean changing phase does not dissolve the soil moisture deficit, the vegetation moisture deficit, and the accumulated dryness that 18 months of La Niña forcing built into this landscape. Those deficits clear on timescales of months to seasons, not weeks. The ocean has already moved on from the pattern that caused them. The landscape is still expressing that pattern in full. And between those two timelines, there is a gap during which the landscape continues to carry a moisture debt that the atmosphere no longer acknowledges, and the forecasting conversation has already moved past. To understand why La Niña produced the specific drought geography it did across the southern United States, you need the basic mechanics. During a La Niña event, cooler than normal sea surface temperatures in the central and eastern tropical Pacific alter the atmospheric heating pattern that drives global circulation, specifically the region of intense tropical convection, the deep thunderstorm activity that acts as one of the primary energy injectors into the global atmospheric circulation, shifts westward toward the warmer waters of the western Pacific and the maritime continent. That shift modifies the Hadley circulation, the large-scale overturning of the tropical atmosphere, in ways that propagate teleconnections into the mid-latitudes. For the continental United States, the documented and well-replicated consequence is a systematic northward displacement of the jet stream across the southern tier of the country. That displacement has a specific precipitation consequence. The jet stream in its normal winter configuration acts as the steering mechanism for mid-latitude storm systems crossing the Pacific and entering the continent. When the jet stream is displaced northward, those storm systems are routed preferentially toward the Pacific Northwest, the Northern Rockies, and the Northern Plains. California, Arizona, New Mexico, the Southern Rockies, and the Southern Plains receive reduced storm frequency, not zero storms, but substantially fewer, and with weaker moisture transport than a more southerly jet stream configuration would deliver. 18 months of that bias applied to a landscape that was already carrying a substantial fine fuel load from the preceding wet cycle represents a systematic and directional forcing of the soil moisture base across an enormous geographic area. Look at what that actually produced on the ground. Soil moisture monitoring networks across New Mexico and Arizona recorded multi-year deficits, accumulating through 2024 and into 2025. Streamflow data across the Rio Grande Basin and the Colorado River tributaries showed declining base flows reflecting the drawdown of groundwater storage that normally buffers against seasonal precipitation variability. Drought monitor designations across the southern plains expanded steadily through the second half of 2025. None of this was anomalous relative to a standard La Niña pattern. All of it was consistent with the expected climate response to the Pacific forcing that was present. The important thing to hold in your mind is that this La Niña drought was not the acute event that produced the 8% humidity reading. It was the preloading event. It was the mechanism that arrived first and worked on the longest timescale, building the base moisture deficit into the soil and the vegetation before any of the more dramatic atmospheric events that followed had occurred. When the January stratospheric disruption locked the blocking ridge in place and the March heatwave arrived, they were not operating on a neutral landscape. They were operating on terrain that La Niña had already been drying for a year and a half. Stay with me here, because the ocean transition matters for a second reason that has nothing to do with what La Niña did during its active phase. It matters because of what the ocean's background state has been doing regardless of the ENSO phase, and this is where the investigation moves into territory that is genuinely without historical precedent. Global mean sea surface temperatures have been running at or above 21 degrees Celsius on a globally averaged basis for more than a year. That threshold, 21 degrees Celsius for the global average, has no precedent in the instrumental record. The global ocean temperature record extends back reliably to the mid-19th century, and prior to the past year, the globally average sea surface temperature had never crossed that value. The most recent period had the ocean running at or above it persistently, not as a brief transient excursion but as a sustained state. Think about what a globally average sea surface temperature actually represents physically. It is not a regional anomaly. It is not the product of a single warm pool in a single ocean basin. It is the integrated thermal state of every ocean basin on Earth, averaged across their combined surface area, which covers roughly 70% of the planet. When that number is at record levels, it is telling you that the total thermal energy content of the global ocean surface layer is at record levels. That thermal energy does not stay in the water. It transfers continuously into the overlying atmosphere through evaporation, through sensible heat flux, through the latent heat carried in water vapor that rises from the surface and eventually releases its energy when it condenses at altitude. The practical consequence for atmospheric dynamics is that a higher energy ocean provides a larger and more persistent energy source for atmospheric anomalies. A blocking ridge over the western United States in a background ocean state of average temperature is drawing on one energy budget. A blocking ridge over the western United States in a background ocean state with no historical precedent in the instrumental record is drawing on a fundamentally different and larger energy budget. The same circulation pattern can sustain itself longer, produce more intense temperature anomalies within the ridge, and drive more extreme evapotranspiration rates than the historical database of similar circulation patterns would predict. This is where the ENSO framework, which has been the organising tool for seasonal climate forecasting in the United States for decades, starts to show its limits. ENSO, meaning the cycle of El Niño and La Niña events, is a real and significant driver of interannual climate variability. Its teleconnections to North American precipitation and temperature anomalies are well documented. The forecasting tools built around ENSO have genuine skill, but those tools were calibrated on a historical observational record in which global mean sea surface temperatures were substantially lower than they are today. The templates that say, a La Niña of a given magnitude produces a certain range of precipitation anomalies across the southern United States, or that an El Niño produces a certain range of winter storminess across California, were derived from decades of observed ENSO events that all occurred in a cooler ocean background state. When you layer a standard La Niña teleconnection pattern on top of a global ocean background that is running at record warmth, you're asking the forecasting framework to extrapolate outside the range of the data it was trained on. The La Niña response it predicts may be in the right direction, but the magnitude, the persistence, and the coupling to other atmospheric extremes may all exceed what the historical templates anticipated, and that is precisely what the record shows. A La Niña pattern that suppressed southern tier precipitation, as La Niña patterns reliably do, but did so in combination with an anomalously warm background ocean that amplified the downstream atmospheric dynamics in ways that pushed the January stratospheric event, the blocking ridge, and the March heat anomaly well beyond the historical envelope of previous La Niña winters. The ocean's phase transition toward neutral changes the forecast. It does not change what has already been built into the landscape, and the landscape is what burns. But there is one more piece of this chain that the ocean's background state connects to directly, and it involves a heat wave that broke temperature records on a scale and at a speed that the standard probability framework cannot accommodate using historical assumptions. The numbers associated with that event do not describe a marginal shift in climate statistics. They describe something closer to a structural departure from the distribution those statistics were built to characterize. March 26th. A temperature station near the California-Arizona border returned a reading of 112 degrees Fahrenheit. Let that register for a moment not as an abstraction, but as a physical fact about a specific place on a specific date in the third month of the calendar year, 112 degrees, in March. That is an absolute all-time March temperature record for the United States, the highest reliably measured air temperature ever recorded on this continent in that month, and it did not occur in isolation. Embedded within the same synoptic event, 14 states broke their all-time monthly temperature records across a span of days. Not their records for a particular week, not their records for a particular year, their all-time records for the month of March, meaning the highest March temperature ever measured in that state since instrumental records began, fell in 14 states simultaneously within the same several-day window. And surrounding those headline records, over 1,400 individual daily records fell nationwide. A daily record means the highest temperature ever recorded at a specific station on a specific calendar date, drawn from the full observational history of that station. 1,400 of those fell in days. Stay with me here, because the statistical structure of that number matters. Daily records fall every year. In a stable climate, the rate at which they fall follows a predictable distribution, because with enough stations and enough calendar dates, random variation produces a certain background rate of record exceedance. What that background rate does not produce is 1,400 records falling across the country in a coherent cluster over a period of days, concentrated in a single month, with spatial patterns pointing systematically in the same direction. That kind of clustering is the observational signature of a large-scale forcing mechanism, not the signature of random variation at the tail of the distribution. The World Weather Attribution Project completed a rapid analysis of the event, and the probability ratio they arrived at was approximately 800 to 1. Here is what that number actually means, because it is easy to hear it as an impressive-sounding statistical abstraction and miss what it is describing. A probability ratio of 800 to 1 relative to a pre-industrial baseline means that the current state of the climate made this specific March heat event 800 times more likely to occur than it would have been before industrialization changed the energy balance of the atmosphere. Not twice as likely, not 10 times as likely, 800 times. Think about what that figure requires in terms of the underlying temperature distribution. If an event was simply becoming more common at the margins, if warming were nudging the probability of warm extremes upwards slightly, while leaving the shape of the distribution broadly intact, you would see probability ratios in the range of 2 to perhaps 20. You would not see 800. A ratio at that magnitude does not describe a marginal shift at the centre of the temperature distribution, where most of the statistical mass lives. It describes a fundamental restructuring of the distribution's tail, the extreme end where the values that determine whether things burn, whether crops fail, whether infrastructure designed for a different climate breaks down. Those are the values that actually matter operationally, and those are precisely the values that have moved. The difference matters enormously for how you interpret what the monitoring record is telling you. If warming was simply adding a uniform increment to every temperature on the distribution, the shape would shift, but the rare events would remain rare relative to the new mean. What a probability ratio in the hundreds means is that the tail has fattened, that the events formerly so rare as to be operationally dismissible are now occurring with a frequency that demands they be treated as part of the planning environment rather than as exceptional anomalies that the system can absorb and recover from. The March heatwave was not an outlier in a stable distribution. It was a signal from a distribution that has changed shape. Now here is where the temperature event becomes something other than a one-day record. The heatwave did not end after March 26th. It did not peak, generate the headline reading, and then dissipate as heat events have historically done in this region. It locked in place. The blocking ridge produced by the weakened polar vortex, the same structure that had already rerouted storm systems away from the mountain terrain through the critical winter snowpack accumulation period, continued to hold the drying conditions in place for weeks. The ridge that prevented winter storms from reaching the mountains did not dissolve when spring arrived. It simply continued doing what it had been doing, holding the atmospheric circulation in a configuration that channeled warm, dry air across the affected states day after day, without the interruption that a normal active jet stream would have provided. The consequence of that persistence for the soil and vegetation moisture state of the region was measured in evapotranspiration rates, the combined loss of water from soil evaporation and plant transpiration, and those rates during this period were consistent with values the monitoring network normally associates with peak summer, August values, running in March, sustained over weeks, without any precipitation input to offset them. The soil moisture decline that the historical record would place in late June or July was occurring in real time during the 3rd and 4th weeks of March, compressed into a window that the agricultural and hydrological monitoring architecture was not designed to track in real time. This is the process that fire and drought scientists call flash drought, and the definition turns on its speed rather than its eventual severity. Traditional drought develops over months. Soil moisture declines gradually. Vegetation stress indicators change slowly enough that the monitoring systems designed to track them, which operate on weekly and bi-weekly update cycles, can document the progression and provide advance warning with enough lead time for management responses. Flash drought does not operate on that schedule. The mechanism driving it, an anomalously warm and dry atmospheric pattern that simultaneously accelerates evapotranspiration and suppresses precipitation, can complete the transition from adequately moist to critically dry in under 2 weeks. Look at the operational implications of that timeline. The United States Drought Monitor, which is the standard authoritative weekly summary of drought conditions across the country, publishes its updates on a Tuesday cycle. Data collection, station verification, model integration, and the expert synthesis that produces the final map all occur within a constrained time window. Under normal drought progression, that weekly cycle is entirely adequate. The drought you are documenting this week is not dramatically different from what it will be next week. The designation you issue reflects a condition that will still be broadly accurate 7 days later. Under flash drought conditions evolving at the rate observed during the March blocking event, the weekly map was documenting a landscape that had already moved beyond what the map showed. The official designation was trailing the physical state of the soils and vegetation by days to more than a week, a gap that is negligible when conditions are stable, but becomes operationally critical when fire risk categories are shifting within the same reporting period. The Drought Monitor was publishing history. The landscape had already crossed thresholds that were not yet appearing in the official record. Here is what that gap means in practical terms. The systems that position suppression resources, that issue public warnings, that trigger utility hardening protocols, that activate fire restrictions, these systems are downstream of the monitoring infrastructure. If the monitoring infrastructure is running behind the physical state of the landscape, the response systems are running behind it too, by at least the same lag and potentially more, given that institutional decisions require time to process updated information before generating action. In a slow onset drought, that lag is absorbed by the margin. In a flash drought completing in 12 to 14 days under conditions the monitoring cycle was not designed for, the margin disappears, and then the wind arrived. The monitoring gap is not a secret. The people who run the United States Drought Monitor know it exists. The hydrologists and climatologists who contribute to it weekly understand that their system was built for a pace of change that flash drought does not respect. This is not a criticism of the people or the institution. It is a description of a structural mismatch between a monitoring architecture designed for one climate regime and a landscape now operating in another. Understanding that mismatch is not optional background information. It is the operational context for everything the wind forecast is about to do to the situation. Think about the specific combination that existed across the central and intermountain states entering the final days of March. A soil moisture base already running at midsummer deficit levels because the snowpack that normally maintained spring moisture never accumulated. A fine fuel loading from 3 consecutive productive growing seasons that had stocked the landscape with biomass at above average density across millions of acres. An evapotranspiration cycle that had been running at August rates for weeks under the blocking ridge, stripping residual moisture from both the soil and the vegetation faster than any historical March drought progression had done. And a monitoring system whose official weekly designations were documenting conditions that the physical landscape had already moved past by days to more than a week. Now add the specific atmospheric mechanism that flash drought research identifies as the most dangerous second-stage forcing. The blocking pattern did not merely sustain heat and dryness, it also set up the pressure gradient configuration that produces the wind event now on the forecast. Here is where the meteorology gets precise and the precision matters. A strong, persistent high-pressure ridge over the western United States does not sit in atmospheric isolation. It interacts with the pressure systems around it, and the gradient between the ridge and adjacent lower pressure areas generates surface winds. When the ridge is anomalously strong, and the adjacent low-pressure systems are correspondingly deep, the gradient steepens. And a steep pressure gradient across terrain like the Wyoming Basin, the Colorado Plateau, and the southern plains, where there are relatively few topographic obstacles to slow boundary layer flow, translates into sustained high surface winds with minimal frictional modification. The forecast calling for sustained speeds of 30 to 40 miles per hour with gusts to 70 miles per hour is not an independent atmospheric event layered on top of the humidity extreme. It is the same blocking pattern expressing itself through a different physical mechanism. The drought and the wind share a common atmospheric parent. Stay with me here, because this coupling is precisely what makes the monitoring gap so consequential. The standard fire behavior models used by federal fire management agencies to predict spread rates, flame lengths, fire intensity, and the suppression resource requirements that follow from those predictions were built on decades of observational data that documented how fires actually behaved across a range of fuel moisture and wind conditions. Those models have real skill within the range of conditions they were trained on. They are not arbitrary. They incorporate physical relationships between fuel moisture content, wind speed, topographic slope, fuel continuity, and the resulting fire behavior metrics that have been validated against thousands of observed fires. But those models have input boundaries. They were calibrated on data from fires that occurred across the distribution of conditions the historical record produced. When every input variable is simultaneously at or beyond the edge of that observational distribution, the models are being asked to extrapolate rather than interpolate. Extrapolation in physical modeling is not impossible, but its reliability degrades with distance from the calibrated range, and the distance here is not marginal. Humidity at 8% combined with gusts to 70 miles per hour, combined with fine fuel loading at the density described by the regional biomass, data does not sit just outside the historical envelope. It sits well outside it, in a combination the models were never populated with observational data to constrain. Look at what that means operationally. Incident commanders making decisions about where to position crews, when to issue evacuation orders, how far ahead of the fire front to establish control lines, all of those decisions are downstream of behavior model outputs. If the model is underestimating spread rate because it is extrapolating beyond its calibrated range, the evacuation timing window it predicts is too wide, the control line distance it recommends is too close, and the resource positioning it supports is based on a fire that will not behave the way the model says it will. The gap between predicted and actual behavior under these conditions is not a rounding error. It is the difference between a crew in a position of manageable risk and a crew in a position from which they cannot escape. The National Weather Service's use of the word erratically in its fire weather language is doing exactly this technical work. It is not rhetorical. It is a formal acknowledgement that the agency's confidence in standard fire behavior prediction has declined because the conditions are outside the range that standard prediction tools reliably cover. Erratic fire behavior is what the modelling community calls the regime beyond which deterministic prediction breaks down, and probabilistic language is the honest alternative. When an agency with the National Weather Service's institutional conservatism uses that word in an official product, it is communicating something specific to the operational fire management community that may not translate its full significance to a general audience. What it is communicating is that the normal relationship between input conditions and output behavior has become unreliable, and that the assumptions built into response planning need to be treated with explicit uncertainty rather than as dependable estimates. Now consider how the monitoring gap compounds this. The fire behavior uncertainty the National Weather Service is acknowledging in its language is a direct function of the input conditions, specifically the humidity and wind values, being at the extreme edge of the observational record. Those input conditions arrived faster than the drought monitoring cycle could document in real time. The landscape crossed the critical fuel moisture thresholds during a period when the official monitoring record was still showing conditions that were severe, but not yet at the level that triggers the highest response postures. By the time the weekly drought monitor update caught up to what the soil and vegetation were actually doing, the atmospheric conditions driving the flash drought had already been running for additional days. The official record, the document that institutional response systems reference when making resource deployment decisions, was describing a landscape that no longer existed. Think about what that actually means for the pre-ignition environment that exists right now. Every operational system designed to detect, characterize, and respond to the conditions that precede a major fire event is working from a description of the landscape that lagged behind reality during the period of most rapid change. The resource pre-positioning decisions made while the drought monitor showed severe but not record conditions, the public communication frameworks triggered by those designations, the utility hardening decisions calibrated to the probability assessments that follow from official drought status. All of these were made against a baseline that the landscape had already left behind. Wyoming utilities making the decision to cut power preemptively this morning are absorbing that lag in real time, calculating that the cost of acting ahead of what the official record fully documents is lower than the cost of waiting for the documentation to catch up. There are 192 active weather alerts across the United States today. 13 of them are red flag warnings. The Storm Prediction Center is carrying critical fire weather risk designations extending to New York and Georgia, a geographic spread of fire weather concern that has no precedent in March across any year in the operational record of that agency. The National Interagency Fire Center is using March language it has never used before. None of these systems are reacting to a fire. There is no fire. All of them are reacting to a pre-ignition environment that exists completely and fully before a single spark. The gun is loaded, and the question the data is now forcing, the one that sits at the intersection of the fuel architecture, the monitoring gap, the model breakdown, and the wind, is whether the fire behavior that results when this environment produces an ignition will look like anything the operational record has documentation for. Because if the answer is no, the implications extend far beyond the question of how today's fire is managed. They reach into the deeper question of whether the entire operational calendar, the one that tells agencies when to preposition, when to warn, when to escalate, was built for a march that the atmosphere has already left behind. 70 miles per hour. Hold that number in your mind, because the instinct when you hear a wind speed in the context of fire is to think about spread. Wind moves fire forward. Everyone understands that. But at 70 miles per hour, something qualitatively different is happening, and if you only think about spread, you are missing the more dangerous mechanism entirely. Start with what wind is doing to the combustion chemistry itself. A fire burning in still air is constrained by the oxygen available in its immediate vicinity. As combustion proceeds, it consumes the oxygen in the local air mass and produces combustion gases that displace fresh air from the reaction zone. The fire is essentially competing against its own exhaust. Under those conditions, burn temperature is limited by oxygen availability, and incomplete combustion produces more smoke and less heat than the fuel is theoretically capable of generating. Now introduce sustained wind at 30 to 40 miles per hour, directed into the reaction zone. You're not just moving the fire, you're continuously flushing the combustion exhaust out of the reaction zone and replacing it with fresh ambient air carrying its full oxygen complement. The fire is no longer competing against its own exhaust. It is running at something approaching its theoretical maximum combustion efficiency. Burn temperatures rise substantially. The reaction proceeds faster and more completely. The fire becomes, in a very specific thermochemical sense, a better fire. More energetic, higher temperature, consuming fuel at a faster rate per unit area than the same fuel under calm conditions would produce. That matters because ignition temperature for adjacent unburned fuels is a function of the heat flux reaching them from the burning material. Higher burn temperatures produce higher radiant and convective heat flux to the fuels ahead of the fire front. Those fuels are already sitting at 8% humidity, already at ignition temperatures 30 to 40 degrees Celsius below their normal springtime threshold. The combination means the thermal work the fire has to do to ignite the next increment of fuel ahead of it has been reduced from both directions simultaneously. The fire is producing more heat per unit area, and the fuel in front of it requires less heat to ignite. The rate of spread that results from that combination is not additive, it is multiplicative. Fire spread rates in continuous grass fuels under documented combinations of low fuel moisture and high wind have been measured at 5 to 8 miles per hour. Think about what that number actually means in operational terms. A structural fire engine responding to an incident travels to the scene. A crew deploys, equipment is positioned, hoses are laid. In the time required to complete those steps from initial dispatch, a fire burning at the lower end of that spread range has already advanced 4 to 5 miles from its ignition point. At the upper end it has advanced further. The fire is not waiting. It does not pause while the institutional response machinery turns over. It is moving at a rate that makes the concept of chasing it with ground resources, in continuous fine fuels under these conditions, operationally incoherent from the first minutes after ignition. But here is where the wind mechanism does something that spread rate alone does not capture. At gusts approaching 70 miles per hour, the convective column above the fire begins to interact with the wind field in a way that produces what fire scientists call spotting. The mechanism is specific. As burning material is consumed, the fire generates an intense convective updraft, a column of superheated air rising rapidly from the combustion zone. Firebrands, meaning partially burning embers and fragments of vegetation, are entrained in that updraft and lofted to altitude. Under calm conditions, those firebrands rise and fall within a short distance of the fire front, sometimes establishing small spot fires ahead of the main front, but rarely at distances that exceed the suppression infrastructure's ability to respond. At 70 miles per hour gusts, the horizontal transport of those lofted firebrands is in a completely different category. The documented spotting distances under high wind conditions place firebrand travel at 1.5 to 2 miles ahead of the main fire front, before the embers contact the ground and ignite new independent fires. 1.5 to 2 miles. A fire that originates along a highway right-of-way, from a vehicle producing a spark against dry roadside grass, does not advance toward a residential subdivision on its leading edge. It teleports into that subdivision through the spotting mechanism before the main front arrives. The subdivision experiences ignition from above, from burning material that fell from the sky, before anyone at the highway margin has had time to report the initial fire to emergency services. By the time the first aerial suppression resource is positioned over the original ignition point, there are multiple independent fires burning 2 miles away in terrain that was not in the initial incident perimeter and is not yet in any operational planning document. Stay with me here, because this is the mechanism that breaks the suppression logic most completely. Standard incident command doctrine for wildland fire is built around the concept of controlling the perimeter. You identify the fire's active edges, you commit resources to the most dangerous sections of that perimeter, and you work to establish control lines that stop lateral and forward spread. That doctrine functions when the fire perimeter is a coherent, identifiable boundary that advances in ways the terrain and fuel conditions make predictable. Spotting at 1.5 to 2 miles under 70 mph gusts means the fire does not have a coherent perimeter. It has a primary combustion zone and a set of independent ignitions distributed across a 2-mile radius ahead of it, each of which is itself capable of generating additional spotting events in the same wind field. The incident perimeter is not a line. It is a probability distribution of potential ignition points extending miles ahead of the flame front, populated in real time by burning embers the wind is delivering continuously. The incident command infrastructure is not designed for that geometry. The resource deployment models, the air tanker retardant drop calculations, the crew positioning frameworks, all of them assume a fire with an identifiable edge that can be approached and worked. Multiple simultaneous spot fires 2 miles ahead of the main front, each establishing and growing before suppression resources can reach them, convert a single incident into a multi-front event faster than any pre-positioned resource package can absorb. The logistics of suppression assume a pace of fire development that the physics at these input values simply does not deliver. Think about what this means for the 192 active weather alerts, the preemptive utility power cuts, the unprecedented March language from the National Interagency Fire Centre, all of which exist before any fire has started. Those systems are trying to reduce the ignition probability in this environment, because the people running them understand that a successful ignition under these conditions does not follow the operational playbook. The utility companies in Wyoming are cutting power not because power lines always start fires, but because in this specific pre-ignition environment, the consequence function of a power line contact with 8% humidity grass in a 70 mph wind field is categorically different from what that same contact produces under any humidity and wind combination in the historical operational record. The measured spread rates, the spotting distances, the combustion efficiency amplification, these are all values derived from the observational record of previous fires. But here is the complication that the data forces into the open. Those measurements were made on fires that occurred across the distribution of conditions the historical record produced. The combination currently present, 8% humidity, 70 mph gusts, and the specific fine fuel loading density that 3 productive growing seasons built into this landscape, does not appear in that record as a concurrent combination. The individual extremes have been approached in isolation. As a simultaneous package, they have not been observed and documented in a way that constrains what the models predict. The fire behavior science is honest about this. When fire scientists describe the transition to erratic behavior, they are describing the point at which the deterministic component of the spread models, the part that says given these inputs you will get this output within a calculable range, gives way to something more probabilistic and less bounded. Not because the physics changes, the physics is fixed, but because the inputs are driving the system into a regime where the feedback mechanisms within the fire itself, the way it modifies its own wind field, generates its own inflow, and builds a convective column large enough to alter the local circulation pattern, begin to dominate the behavior in ways that are not captured by models trained on smaller, less energetically extreme events. And this is where the landscape scale flashover analogy, the one fire scientists use when they want to describe what happens when the accumulated thermal and fuel conditions cross a specific threshold simultaneously, stops being a metaphor and starts being a physical prediction. The question is not whether the models are imprecise at the margins. The question is whether the conditions present right now are sufficient to push a fire in continuous grass fuels across the threshold from a combustion event into something that generates its own atmospheric dynamics. And the uncomfortable answer that the data presents is that the combination of inputs on this specific morning sits precisely in the range where that transition, the one the models were never built to describe, becomes reachable. The word erratically appeared in a National Weather Service fire weather product this morning. One word buried in technical language that most people reading the forecast will not pause on. But in the operational vocabulary of federal fire meteorology, that word is not a casual descriptor, it is a threshold marker. It is the point where the agency's confidence in what the fire will do next has declined past the level where deterministic language is still honest. When the National Weather Service uses the word erratically in an official product, it is telling the incident commanders, the dispatch coordinators, the crew supervisors, and the aircraft pilots who depend on that language to make decisions about where to stand and where to fly that the standard predictive framework is no longer fully reliable. That is a specific and significant communication, and it deserves to be understood precisely. Here is what erratic fire behavior actually means in the physical sense. A fire burning within the normal range of documented conditions behaves according to relationships that the science has characterized well enough to produce useful predictions. Given fuel moisture at a certain value, wind at a certain speed, slope at a certain angle, fuel continuity of a certain type and density, you can apply the standard spread models and arrive at a spread rate estimate, a flame length estimate, and a spotting distance estimate that will be within a useful range of what actually happens. Not perfectly accurate. Fire is a complex system, and the models acknowledge that with confidence intervals. But accurate enough that the incident commander positioning a crew can make a defensible decision about safety margins. Accurate enough that the evacuation timing window the model produces is close enough to reality that people get out. Erratic behavior is what the modeling community calls the regime beyond that. It emerges when the fire transitions from being primarily driven by the external conditions fed into the model, the fuel moisture, the ambient wind, the topography, and begins to generate its own internal dynamics that feed back on those inputs. Stay with me here, because this feedback mechanism is the critical concept. At sufficient combustion intensity, a fire builds a convective column above itself. Not a passive plume of smoke drifting downwind, but an active, organized convective structure in which the heat released by the fire drives a rapid atmospheric updraft that pulls surface air inward toward the combustion zone from all directions. That inflow creates its own surface wind field, one that is not necessarily aligned with the ambient wind and can actually oppose it in some sectors around the fire perimeter. The convective column, if the fire is sufficiently energetic, can extend tens of thousands of feet into the atmosphere and begin interacting with winds at altitude that have completely different speeds and directions than the surface winds feeding the fire from below. When the column collapses, and intense convective columns do collapse, the air that has been drawn up and lofted crashes back toward the surface in what meteorologists call a downburst, generating sudden localized wind speeds at the surface that bear no predictable relationship to the ambient wind forecast. A crew positioned in what the model indicated was a safe sector, relative to ambient wind, can be in the path of a downburst from a collapsed convective column. That event is not in the model. It is a self-generated atmospheric phenomenon that only exists because the fire has become large and energetic enough to build the column that produced it. Fire scientists describe the broader transition using a specific analogy, and it is worth working through it carefully because it is not rhetorical. In a structural fire, there is a documented threshold event called flashover. In the initial stages of a room fire, individual items burn independently. Heat accumulates in the upper portion of the room, and the fire's spread is relatively controlled and predictable. As the accumulated heat in the upper room layer reaches a critical threshold, every combustible surface in the room that has been preheated to near ignition temperature ignites simultaneously. The room does not continue burning. The room becomes fire. The transition from sequential spread to simultaneous full room involvement is nearly instantaneous, and the behavior of the fire after flashover is categorically different from its behavior before it. Standard structural firefighting doctrine does not allow crews inside a room that has flashed over, because the environment inside that room is no longer survivable, and its behavior is no longer manageable. The landscape scale equivalent of that transition is what fire scientists are pointing at when they use the analogy in the context of conditions like today's. When fine fuel loading is dense and spatially continuous, when humidity is low enough that ignition temperature thresholds across that continuous fuel bed have been uniformly reduced, and when the wind field is delivering enough oxygen at high enough velocity to push combustion toward its theoretical efficiency maximum, the accumulated energetics of the system can cross a threshold where the fire is no longer primarily a surface combustion event spreading through fuel. It is a coupled fire-atmosphere system generating its own dynamics, and those dynamics include wind speeds the ambient forecast did not predict, convective column behavior that the spread models do not capture, and ignition events at distances the spotting models were not calibrated to anticipate. Think about what that actually means for the pre-ignition environment this morning. The 192 active weather alerts exist before any fire has started. The preemptive utility power cuts in Wyoming are absorbing certain economic loss to reduce a probabilistic risk that has not yet materialized. The unprecedented March language from the National Interagency Fire Center is describing a potential, not an event. All of that institutional response is happening because the people responsible for managing the consequences of ignition understand that what follows a successful spark in this environment may not follow the operational script. Look at what the operational timelines actually require. An incident is reported. Dispatch receives the notification. Resources are mobilized. Air tankers require a certain lead time to reach an operational position over an incident. Ground crews require travel time to the incident perimeter. Evacuation orders require time to reach residents through the alert systems, and residents require time to physically clear the threatened area after receiving the order. Every one of those timelines was calibrated against a fire behavior envelope that assumed a relationship between ignition and the subsequent rate of threat expansion that the historical record supported. A fire that spreads at 5 to 8 miles per hour in continuous grass fuels is already stressing those timelines. A fire that's simultaneously generating spot fires 1.5 to 2 miles ahead of its main front is overwhelming them. And a fire that has transitioned to coupled fire-atmosphere behavior, generating its own wind field, building a convective column that interacts with upper-level winds, and collapsing that column unpredictably onto terrain that the incident perimeter does not yet include, is operating on a timeline that the response infrastructure was never built to match. Here is where the data assembles into its most uncomfortable implication. The seasonal fire calendar, the one that tells the National Interagency Fire Center when to begin moving air tankers from winter storage to pre-positioned bases, when to staff up the dispatch centers to peak capacity, when to issue the public communication campaigns that remind people living in fire-adjacent terrain to clear defensible space and know their evacuation routes. That calendar was built on a body of observational data about when fire seasons historically began and how quickly they historically escalated. It encoded the march of a previous atmosphere, the one in which 8% relative humidity across 4 states simultaneously was not a reading the sensors returned in late winter, the one in which the snowpack was still releasing meltwater into the soil through May and June, the one in which the fine fuel moisture content that makes ignition almost trivially easy was a July phenomenon, not a March one. That calendar is not wrong because someone made a mistake. It is running behind because the baseline it was built on has moved, and the distance between the old baseline and the current one is not a marginal statistical adjustment. It is the distance between a March that historically did not produce these conditions and a March that demonstrably does. The monitoring systems, the response timelines, the resource deployment schedules, and the public risk communication frameworks are all downstream of that calendar. If the calendar is behind the fire season, every system it drives is behind the fire season by at least the same margin. The 192 alerts, the 13 red flag warnings, the critical risk designations reaching anomalously to New York and Georgia, the preemptive power cuts, the unprecedented March language. These are the operational systems straining against that lag in real time. They are not reacting to an event. They are reacting to a pre-ignition environment that fully and completely exists before the first spark, and they are doing so using institutional frameworks that were designed for a threat posture that arrived in summer, not in the 3rd week of March. The data assembled across this entire investigation, from the ocean temperature baselines, through the stratospheric disruption, through the snowpack failure, through the flash drought completion, through the fuel moisture collapse, resolves into a single finding, and that finding does not describe something that went wrong. It describes something that has changed. The answer to what the data means is not in any single anomalous reading. It is in the chain those readings form, and what that chain says about the seasonal architecture the response systems are still assuming they are operating inside. The chain is now complete. Every link is visible, and the most important thing the data is asking you to do, at this point in the investigation, is resist the temptation to treat what you have just seen as a sequence of compounding bad luck. It was not luck. It was not a pile-up of independent anomalies that happened to arrive simultaneously through some improbable atmospheric coincidence. It was a mechanistically coupled sequence in which each stage created the physical preconditions for the next, and the whole chain ran from the global ocean through the upper atmosphere, through the mountain snowpack, through the soil, through the grass, and arrived, with the logic of a proof, at 8% relative humidity in March across 4 states at once. Here is what that actually means. The elevated global ocean temperature provided the background energy surplus that amplified the atmospheric response to La Niña beyond what the historical ENSO templates predicted. La Niña displaced the jet stream northward and built the base moisture deficit into the soils of the southern tier over 18 months. The sudden stratospheric warming event in January disrupted the polar vortex and allowed the jet stream to develop the blocking ridge that rerouted winter storms away from the mountain terrain during the critical snowpack accumulation window. The blocking ridge brought anomalous warmth that displaced the rain-snow line upward, converting precipitation that would have been stored as snow into rain that left the system within days. The snowpack that did not accumulate could not release the meltwater that soils entering spring would have depended on to carry their moisture baseline through the early growing season. The anomalous March heat, locked in place by the same blocking ridge and amplified by a background ocean state, with no precedent in the instrumental record, drove evapotranspiration at peak summer rates for weeks across terrain that had no moisture reserve to draw on. The flash drought that resulted completed faster than the monitoring system designed to track it could document in real time, and the fine fuel loading built by 3 consecutive productive growing seasons was sitting across millions of acres of that terrain, fully stocked and fully prepared when the humidity sensors returned 8. Every link followed from the one before it. The chain is not a coincidence, it is a physical argument. Think about what that actually means for how you interpret the probability ratio the World Weather Attribution Analysis produced. 800 to 1 relative to a pre-industrial baseline. That number is commonly understood as a statement about a single event, the March temperature record, becoming more likely in a warmer climate. But what the chain assembled here suggests is that the 800 to 1 ratio, large as it is, may actually be the most conservative way to frame the anomaly, because it describes the probability of the temperature event in isolation. What the chain shows is that the temperature event was not operating in isolation. It was the 5th or 6th link in a sequence that was already coupled and already running. The probability of the entire coupled sequence, ocean baseline plus La Niña amplification, plus stratospheric disruption, plus snowpack failure, plus flash drought, plus the temperature record, occurring together as an unbroken physical chain is not calculated by the rapid attribution framework because it was designed to assess individual events. But the directional implication is that the sequential coupling of these mechanisms makes the terminal condition, the 8% humidity in March, substantially less improbable than any single link in the chain would have suggested on its own. The links reinforce each other. They were not independent rolls of the same die. Stay with me here, because this is where the data stops being a description of the past and becomes a statement about the present architecture of the climate system. What the chain demonstrates is not that an extreme event occurred. Extreme events have always occurred. What it demonstrates is that the mechanisms capable of coupling into this specific terminal sequence, ocean warming, ENSO forcing, stratospheric disruption, blocking persistence, snowpack failure, flash drought, are all simultaneously present in the current climate system and are interacting in ways that the historical observational record did not produce frequently enough to calibrate the forecasting and monitoring tools against. The chain is not a once-in-a-generation curiosity. It is a pathway that the current atmospheric state has made more accessible than it has ever previously been, and every component of it is traceable to physical forcings that are not resolving. The ocean is not cooling. The stratospheric variability associated with a disturbed polar vortex is not declining. The fuel architecture built by the preceding wet cycle is present across the landscape right now. Look at what that means for every operational system that has not yet been rebuilt around this shifted baseline. The seasonal fire calendar encodes assumptions about when the critical fire weather window opens. Those assumptions were derived from decades of observational data in which the calendar held. Snowpack persisted into May. Soil moisture carried through late spring. Fine fuel moisture content below dangerous thresholds was a summer phenomenon. The calendar that resource deployment schedules, drought monitoring update frequencies, utility grid hardening timelines, and public risk communication frameworks were all built on reflected that reality faithfully. It was not a bad calendar, it was a calendar for a different March. The March. The calendar was built for still exists in the planning documents, in the pre-positioning schedules, in the staffing curves at interagency coordination centres, in the update cycle of the monitoring systems. The March the atmosphere delivered this year does not match those documents. The gap between them is not a planning failure. It is an information failure of a specific and structural kind, one in which the baseline has shifted faster than the institutional frameworks designed around it have been updated to reflect. That gap has operational consequences that are not abstract. They are measured in the distance between where the fire behaviour models say the perimeter is and where the perimeter actually is, in the time between when the evacuation order is issued and when the spotting mechanism has already placed burning embers 2 miles past the evacuating population, in the difference between a resource pre-positioning schedule calibrated to a June fire season and a fire environment that is fully developed in the last week of March. The 192 active alerts, the preemptive power cuts, the unprecedented agency language, these are not overreactions to a bad forecast. They are the operational systems attempting in real time to compensate for the lag between the shifted baseline and the institutional framework still calibrated to the old one. They are the systems straining against the gap, and the fact that they are straining before any fire has started, before a single spark, is the most precise summary of where the investigation has arrived. Here is the resolution. The 8% humidity reading that opened this investigation is not an outlier requiring special explanation. It is the logical terminal output of a coupled physical chain whose individual components are each traceable to forcing mechanisms that are now more probable than their historical baselines, by factors ranging from dozens to hundreds. The anomaly is not in the reading. The anomaly is in the assumption that the reading should have been surprising. It was not surprising if you were tracking the chain. It was, in a specific and verifiable sense, the expected outcome of a sequence that was already complete. The atmosphere delivered what the physics, assembled in that particular sequence, required it to deliver. The question the data leaves open is not whether this chain can run again. It is whether the operational infrastructure, the calendars, the monitoring cycles, the behaviour models, the response timelines, the public warning frameworks will be rebuilt around the chain that is now documented, or whether they will continue to be calibrated to a march that the atmosphere has already left behind. The landscape does not wait for the calendar to catch up. It is already where it is, and right now it is at 8.